Okay. All right, so what we're going to be reviewing during this session is the electrical chapter. So let me jump over to that. Oops. I'm opening it up in my computer and I'm not sharing the screen here. I guess I ought to follow the way it works. Okay, so cycles per second, anybody who wants to shout in there, cycles per second are referred to as what?
Hertz.
Hertz, there you go. Hey, Destiny.
Hey.
And prior to the 1970s, when they started with these different terminologies that were named after dead white scientists, it was just referred to as cycles per second. But now we have Hertz. All of these terms, Hertz, ohms, newtons, joules, those are all named after, as we always like to say, dead white scientists. So, when a string of batteries is connected in series, what is the answer there? What happens?
The voltage increases, but the amps remain the same.
Right, yeah, this is one of those things where there's just no way of knowing it except to remember it. Oops, I said the voltage and amps remain the same. No, yeah, voltage increases. So with a series connection, when you're hooking them up in series, you're going to be increasing the voltage. It's a cumulative. So if I have two 12-volt batteries and I want to hook them together, I'm going to have a nominal 24-volt circuit. If I have 3, it's going to be 36. If I have 4, it's going to be 48, and so on and so forth. So series is always going to be increasing the voltage. Parallel, as we'll see in future questions, the voltage remains the same, but the amperage increases. So what would be the reason for that? Well, typically, you're going to hook things together in series so that the voltage is compatible. For instance, if you've got a 48-volt system, you need your batteries to be 48 volts, and you need your solar array to be 48 volts nominal. So you would hook them up in series to get to that. But you would hook them then up in parallel to produce more power. You know, you need more power to service the load. So now I'm going to have, say in a battery bank, 4 12-volt nominal batteries will give me a 48-volt system. So my loads might be based on 48 volts or whatever, but I might need twice as much power as that battery will provide. So I'm going to hook up 4 batteries in series, another 4 batteries in series, and then I'll connect those together in parallel, positive to positive, negative to negative. So a series connection is always going to be positive to negative, positive to negative. You can think of it like those old flashlights that had the D batteries that just slid down in the tube. Every time you slide them down, the positive terminal is touching the negative terminal of the next battery. So you needed 4 of them to get the system up to 6 volts because each of those batteries was 1.5 volts. So that's...
Jay, I have a quick question about that.
Sure.
When you're installing a system in a house and let's say they need 240 volts to run like higher appliances, would you have to string your panels in a way that you could get 2 legs of 120 volt power, or can you? No.
No, because it's going to be in the inverter when it's transferred from DC to AC that the voltage conversion takes place, where not only is it converted from DC to AC, but it's converted from whatever the voltage is that's coming in to 240 volts output, or 120 volts if it's a smaller standalone system. So,
Okay.
So it's becoming compatible with your household at the inverter. It really doesn't care what's coming into it to that point, except the inverter has certain specifications for input as well as for output. So oftentimes with grid-tied inverters, they might operate within a voltage range that might be, let's say the minimum that they need is 100 volts, but the maximum they can operate at is 600 volts. So that would be the DC range coming in. But when it leaves, if it's connected to the grid and it's single phase, it's going to be 240 volts. And not only does it have to match the voltage of your house, but it has to match perfectly the voltage of the grid that it's connected to, because you're going to be pumping electricity back onto the grid if you're grid tied. And that changes millisecond to millisecond. You know, the voltage wavers a little bit, it goes up, it goes down. The hertz, the cycles per second, varies between like 59.9 to 60.1. All of those things are changing millisecond to millisecond, and the inverter has to keep up with all of those changes. So every bit of power it puts to the grid matches the grid's, you know, power signal exactly as it's being put onto the grid. Otherwise, you get harmonic distortions on the grid, and it will really mess up the grid. You know, if you think about the grid as a single waveform, if you start throwing dirty power out there, it's going to be more like a choppy sea instead of a wave, instead of a clean wave.
Okay. Practically speaking, would you want to always wire them in series just so your amps stay down and you can use a smaller wire, like a higher gauge wire?
Exactly. Yeah. Well, that's one of the reasons.
Okay.
But there are limits, because the National Electrical Code says you cannot exceed on a residential installation 600 volts. So,
okay.
so they put that as an upper limit. They claim for safety reasons, but nobody seems to quite know why. In Europe, that upper limit is 1,000 volts. And in commercial systems, it's mostly like 1,500 or 1,000 volts. The higher you can go with voltage, the lower the amps are going to be in your system, which means, as you point out, smaller wire, fewer connection points, fewer breakers. So actually, if we were to raise the voltage from 600 volts to 1,000 volts here in the US, estimates are that the cost of an installation would drop by about 20%. So higher voltage is good. And higher voltage is not more dangerous. You know, in the electric, they'll always say it's the amps that'll kill you, you know? So if you go out and touch an electric fence, it may be operating at 3,000 volts, but the amps are so tiny, it's not going to kill you. It's going to feel like a mule just kicked you in the shoulder or whatever, but it's not going to kill you. Now, that said, what will kill you is a combination of voltage and amps, you know? So with a voltage that's so low it can't penetrate the skin, then amperage will not be the problem. But it's mostly the amps that'll kill you.
Okay, nice.
The document that details industry best practices from a safety perspective is?
National Electric Code.
Yeah, the NEC, our buddy, the NEC. And the interesting thing about the NEC, it is from a safety perspective, it does not care if your system works. It, you know, it's not a performance-based thing. And we've had a number of situations in solar where the National Electrical Code comes out with a ruling. For instance, they said back in 2014, when you turn off the solar array at the disconnect switch, at the main AC disconnect switch, we want it to disconnect at the array. And tell you what, let me just show you here in a drawing what I'm talking about. Because what would happen in a typical home, let's say this is the roof line, and you've got your solar array up on the roof. Well, what would typically be designed is, if this is the house, I'm gonna make myself a really bad drawing, but normally you might find the electric meter is gonna be out here, and you want your main AC disconnect, it's gotta be within 10 feet of that meter, so that when the utility people come or the first responders come, they know where they can shut off your array. Because normally what the first responders are going to do is they're going to come in and they're going to pull the meter. like let's say your house is on fire. That's the first thing they're going to do because they don't want there to be any electricity present in the home, because they don't want to electrocute themselves as they're in there trying to fight this fire. They're going to douse it with water. They're going to be chopping through walls with axes and things like that. So they don't want there to be any power. But unfortunately, you have power coming from both directions. You have power from your array and you have power from the utility. So if they just pulled the meter, well, what would happen? Well, typically there's going to be some wire. It's going to be inside the house. It might come down the outside. It'll come, say it comes over here to a DC disconnect. Then it goes inside the house into the basement to the inverter. And then it would come back outside to the AC disconnect, and then it would come back inside the house and connect in to the service panel. So this would be fairly common, and oftentimes these things are located in the basement, the inverter and the service panel. So what's going to happen on a sunny day? They come here and they disconnect it right here at the AC disconnect. Well, it's the inverter that senses that the grid has been lost and shuts down. But all of the wires that are traveling all the way to the DC disconnect and then from the DC disconnect to the inverter, those are still hot. They're still live. They could still be generating, 600 volts, however many amps, 30 amps. And so let's say a fireman climbs up on the roof and he takes a chainsaw or an axe and decides to cut a vent hole right through the roof to vent out the smoke. And he cuts through a live wire that is running at 600 volts, and he's dead, as soon as he does that. So the National Electrical Code said, when we turn this thing off, when we shut this off, we want the array to stop producing power at the array. And in 2014, the industry said, well, how do we do that? And the NEC said, that's really not our problem. Make it happen. So there was no solution. So what's interesting in this case, this regulation led to some innovation that has completely transformed the industry. And that led, well, the first solution was they had a combiner box that was right here, and they basically put a little panic button. So when you punch the button, it disconnected at the combiner box, which was good enough. So it was a remote disconnecting combiner box. But then somebody got the bright idea to say, well, if we put the inverter, if we made a little inverter that attached to each panel, then the inverter is going to sense it and turn off at the array. So that led to the invention of the microinverter. So microinverters have become quite popular. Basically, every panel has a little inverter attached to it, and those inverters, convert from DC to AC, so there is no DC wiring. But then somebody else, in fact, a company called SolarEdge, said, well, these are pretty expensive. Why don't we just not put the inverter up there, but we'll put all the other things that inverters do, including sensing that the grid is shut down and turn off. So what that led to was the invention of the power optimizer. And both of these, microinverters, power optimizers, those are all known as module level power electronics. Basically what they're doing is they're putting an electronic device on each solar panel. So now that when it loses sight of the grid, when you turn off this AC disconnect, the power is stopped right at the panel, right at the array. And that was purely because of the regulation. And this is all referred to as rapid shutdown. We'll talk about this quite a lot later. Anyway, rapid shutdown, you get the idea. This pen doesn't like to draw very well or write very well. Okay, so that's kind of just a long way of explaining that it is the NEC that sets the safety standards, and they are not about performance. Okay, when a number of solar panels are connected in parallel, what happens?
Voltage remains the same, but the amps increase.
That's right, voltage remains the same, but amps increase. All right, and the only way, if you're trying to think of some way of remembering which is which, series is voltage, amps, I always think there's an A in the word parallel. You're like, okay, there's an A there for amps. I don't know if that helps, but it's some little device to think about. Which of the following is not relevant to DC circuits? Resistance, Hertz, Ohm's law, or voltage drop?
Hertz.
Hertz, right? Because the signal, the waveform for DC is just a flat line, right? And Hertz is cycles per second. There are no cycles, so it's not relevant at all to DC circuits. A system designed to eliminate all unwanted current from non-current carrying metal components is referred to as?
Bonding and grounding.
Yeah, bonding and grounding. And this is important. This is a life safety thing. And when we're talking about metal components, non-current carrying metal components, we're really talking about any metal in the system. It could be the panels themselves. It could be the racking, could be the conduit. Good example in our house, we have metal countertops in the kitchen. And Annie was telling me one time that the microwave was giving her a shock, you know, and she wanted me to look at the microwave. And I was saying, is it like static electricity? And she's like, no, it hurts. So I went in and I touched it and didn't feel anything. So of course I thought, okay, she's exaggerating. And then she said it did it again. So I tested it again. There was no problem. Of course, then I was, uh-oh. Looks like okay, it signed me out. What's going on here? You guys still hearing me?
We can hear you,
Yep.
I can see you, and you're on chapter 4 review quiz. Now you're moving.
Yeah, it's telling me that it signed me out. So, all right. It's, as long as I'm still in, I'm not going to mess with it. Okay, so anyway, it turned out what was happening is the tea kettle, the little electric tea kettle, was shorting out down below, and there was a bare wire touching the metal counter. So basically, the entire metal counter was an electric current. And I wasn't getting shocked because I was wearing tennis shoes. I was insulated. But she was getting shocked because she was now a conduit of that electric current to the ground when she touched anything metal on the countertop. So you wouldn't think normally you have to bond and ground your countertops. But that would have been the solution. You want to provide a better pathway to the ground than the human body, you know, and wire is a better pathway to the ground than the human body. So you're going to bond everything together, make an electrical connection between every piece of metal, and then provide a pathway to the ground. And that's known as grounding and bonding. Okay, when referencing the resistance characteristics of various conductors or wires, the NEC measures in the following units.
Ohms per 1,000 feet.
Yeah, ohms per 1,000 feet. So when we get into the voltage drop equation, you're going to see that comes into play. So, and everybody loves the voltage drop equation. So, all right, the amount of flow or current is measured in what?
Yeah.
In amps, right? So you can think about watts and amps. There's the power equation is watts equals amps times volts. So if you think about watts as the amount of water flowing through a pipe, amps is the size of the pipe. and volts is the pressure under which that water is flowing. So the amount of flow that comes through that pipe is a combination of the pressure and the size of the pipe. So the bigger the pipe, everything else held equal, the more power you're going to get, the more water will flow. The bigger the pressure, everything else held constant, the more power you'll get. So you can have a low pressure, big pipe generating the same amount of water as a high pressure, small pipe. So these things are just a relationship, but amps is the current or the size of the pipe. And volts is the pressure. Now we say that, and that's a good analogy, but it's not 100% true. Voltage is really the differential in potential between two things. So that's why when you rub your feet on a carpet on a winter's day, you're basically scraping electrons off your feet. You're creating yourself positively charged because you've lost the negative charge of the electrons in comparison to the surrounding area. So when you touch a doorknob or your brother's ear or whatever it is you're doing, you're going to arc and there's going to be a static discharge to equalize that potential. You know, now everything's become equalized. Okay, an 8-foot long metal rod, commonly called a ground rod, is more accurately referred to as?
Grounding electrode.
Yeah, the grounding electrode. And in residential systems, we often have ground rods, but you don't have to. You know, like in commercial systems, often they'll have what they refer to as an oofer ground, where the rebar that's located in the slab of the building is actually your grounding connection. So they might build it as they're building the slab with a grounding bar, you know, that's attached to all of the rebar that's in the concrete down below the ground. You can use buried wells. You can use, you know, the well casing as long as it's metallic, buried tanks, but I would not recommend you use a petroleum tank or a natural gas pipe. Those are bad grounds because they can explode, you know, so don't use them. But a water tank, a water pipe, those would work. All right. Ohm's law. Ohm's law is expressed as
Current times resistance.
yeah, volts equals amps times resistance. And that's, I always think of Ver, you know, just the equation Ver. So if we say Ver volts equals amps times resistance, all right? So this is Ohm's law, Ver. And then there's also the Ohm's law pyramid if you don't want to know algebra, where you can do volts, amps, and resistance. So if you want to know what volts is, just amps times resistance. If you want to know what amps are, it's volts divided by resistance. If you want to know what resistance is, it's volts divided by amps. So all Ohm's law is expressing a relationship. That's all it is. So that's it, and it's really similar to if I say watts equals amps times volts. These are expressing a relationship as well. And these are two of the equations that you're going to need to remember for the examination, for the certification exam. The power equation, watts equals amps times volts, and Ohm's law, volts equals amps times resistance. There's a third equation that we'll get into, which is a variation of Ohm's law. And in that, it's the voltage drop equation. And that's voltage drop equals amps. And normally when we're talking about solar, we're talking about the IMP, the amps at the maximum power point, times resistance, times twice the distance, divided by 1,000 feet. Well, why are we doing this? Well, if you notice, this is just simply Ohm's law, but the resistance is given to us in the National Electrical Code, and it's given to us for the different wire sizes in units in ohms per 1,000 feet. So we have to know how many thousand feet we have in order to calculate how much our voltage drop will be. So why do I say twice the distance? It's because if I have a wire that's going from here to there, there are actually two wires. It's actually a circuit, right? The electricity always flows in a circle. So if my wire connection is 1,000 feet long, I actually have 2,000 feet of wire that the electricity is traveling through for the potential of voltage drop. So we have to calculate both the positive and the negative legs in the DC system, or one of the hots and the neutral in an AC system. So we do twice the distance divided by 1,000, which is basically Ohm's law, right? Volts times amps times resistance, but we have to modify it based on the fact that there's two wires and it's per 1,000 feet. So hopefully that will make sense to you. As I'm transitioning screens, any questions on that particular nugget of wisdom? Okay, when there's an imbalance between positive and negative charges, such as the terminals of a battery, there's a difference in electrical potential. This difference is measured in
Volts.
volts, that's right. And in fact, one of the most famous scientists of the 18th century, Benjamin Franklin, is the one who determined that positive and negative were two parts of the same phenomenon. Prior to that, they thought they were two separate things. And actually, Benjamin Franklin invented the term battery, because he said when you hook these things up together, you get increased power like a battery of cannons on the wall of a fortress. So that's where the term battery comes from, in case you're wondering, right? So much trivia. When seeking to decrease the effective voltage on a circuit, which of the following is not an effective solution?
Using a smaller diameter wire size.
Right. So when we're trying to reduce voltage drop, we basically could shorten the length of the circuit. We could increase the voltage of the system. That doesn't decrease the amount of voltage drop, but it decreases the effective voltage drop on your system. So for instance, if I have 10 volts that I'm losing over this circuit, if I'm operating at 600 volts, I've only lost 10 over 600, whatever percentage that is. It's like what, 1.5%? But if I'm operating at 12 volts, I've lost almost all my voltage, all my power. So by increasing the voltage, we decrease the effective voltage drop on our system. Or we could pick a wire with better conductive properties. In this case, it would be usually copper. You know, we would pick copper versus aluminum. There are also some high conductivity wires, but that, for our purposes, we don't get into. Okay, which of the following is not a safety recommendation when working with electric wires?
Wearing a respirator.
Yeah, where if you did that on the job, you would be the geek, you know, everybody would make fun of you. Wearing, of course, in today's world, you'd be wearing a mask anyway, so I guess you could get by with it. Yeah, you always want to check to see that the exposed wire to make sure there's no current present. Wear goggles because of arcing, you can always get that. Protective gloves, insulated shoes, that's always important. When a circuit is closed, what happens?
Electrons can flow through it.
Right, so a closed circuit is a light switch that's turned on. So if you think about it, typically, we have, when you're looking at an electrical diagram, let's say that we have a circuit and here is our battery, and we're wanting to go up, we want to connect up to a load. Let's just say here it's going to be a light bulb. Well, a closed circuit, this would be your closed circuit, right? The electrons are flowing from the negative terminal to the positive terminal. The way batteries work is there's an abundance, an overabundance of electrical charge over here. There is some sort of barrier here. You've got the anode and the cathode side, and that electron wants to travel through here and recombine, so it goes to a state of neutrality. When we have a completely balanced battery, what do we refer to that as? That battery is dead, right? You recharge a battery by creating an imbalance. So when that has reached a state of balance, it's a dead battery. It doesn't function any longer. So now if I were to connect the positive and the negative without a load in here, we would then discharge everything all at once, and you would get a lot of burning wires and a lot of sparks. So the load itself regulates the flow of the discharge or the rebalancing. So you have to have a load between these terminals, otherwise you're going to get a short circuit. But oftentimes we're going to want to put in a some sort of switch, because you don't want it on all the time. So we would come here and we would come here, and really at this point, it's an open circuit, right?
Mhm.
No light is coming from that because it's turned off. So when we want it to turn on, we would then close the circuit. And what that does is makes a physical connection between the two wires. And that's all a light switch does. Just makes that physical connection. So now this is a closed circuit, and now the electrons can flow through the circuit. So very basic process, but it seems counterintuitive that a closed circuit is turned on and an open circuit is turned off. For some reason, I think it may be the German in me that thinks that closing the light should be turning it off. So, all right, 6 panels are connected in series. Each panel has a VMP rating of 18 volts and an IMP of 8.33 amps. What is the output current of this string?
8.33 amps.
Yeah, well, that's a good hint because there is only one answer that's in amps, which is the only current, yeah. But remember, when you hook up in series, voltage increases, but amps remain the same. So we could hook up 20 panels together. Amps are still going to be 8.33. We could hook up 20,000 panels together. Amps will still just be 8.33. But the voltage will have increased dramatically. Okay, so bare wire or green insulation will always indicate that that wire is part of
Ground.
A grounded bonding.
Yeah, the grounding and bonding system. Now, the grounding and bonding system is there to take unwanted electrical current from your system to the ground. So there should not be any current on that grounding and bonding system if everything's functioning properly. It's only there in case of emergency. So, but it is green or bare. The loss of an electrical signal over distance as it travels along conductors due to resistance is called
Voltage drop.
voltage drop, right? And we combat voltage drop by putting in bigger wire. That's usually the way we're going to do it. Shortening the distance. Often you're going to try and design your system so the distance is as short as possible anyway. Or using better wire. Or increasing the voltage of our system. Or keeping the wire cooler. Can you usually do that in a situation? Can you control the temperature of the planet, of the world? Often you can. Put the wire in the shade underneath the array. Don't put it in direct sunlight. Bury it in the ground. That will keep it cooler than leaving it exposed to the air. So there are some ways you can keep your wire cooler. More people are killed each year in the US working on what kind of systems?
Regular household electrical.
Residential, like household electrical.
Yeah, regular household. Now that may be a little bit because most people are working on residential household systems. I mean, more people are working on them. But oftentimes with electricians, they get cavalier about it. You know, they're just working with 240 volt systems. They're like, yeah, whatever. You know, well, when you get complacent, that's when you get hurt. 60 watt hours equals what? 6 kilowatts.
240 watts. 240 watts consumed for 15 minutes.
That's correct. So it's easy to figure out watt hours if you just remember that watt hours is watts times hours.
Mhm.
So if I say 6 kilowatts, which is 6,000 watts times 10 hours, well, that'd be 60,000 watt hours. Here it's 240 times a quarter of an hour, or 60 watt hours. This one, 60 watts times 24, well, that's going to be what, 1,200 and something? And then 120 watts for 2 hours is going to be 240 watt hours. So watt hours is just watts times hours. What percentage of power loss due to voltage drop from a 48 volt circuit with an 8.23 volt loss?
It's like 17%.
Yeah, this is going to be 17%. Now in the book, this follows a question that makes it make more sense, because what we're really finding out is after we've calculated voltage drop and we find out it's 8.23 volts, well, how much power have we just lost? So in this case, this is the question: what is the voltage drop of a 400-foot cable run using 10 gauge stranded copper on a circuit designed to carry 8.3 amps and 48 volts of electricity? So the first thing you need to know is, well, what equation are we going to use?
The voltage drop equation.
Right, and the voltage drop equation,
Amps
voltage drop equals amps. Well, we have amps
times resistance.
times resistance. Well, we look up resistance, number 10, stranded, 1.24 ohms per 1,000 feet. So now we've got 8.3 times 1.24 times twice the distance,
800.
800 divided by 1,000. So that'd be basically 0.8. So we take 8.3 times 1.24 times 0.8, and we get?
It's 8.23 volts.
That's right. Yeah. So it's 8.3 times a little more than 1. So here's how it works itself out. Voltage drops equals amps times resistance times twice the distance divided by 1,000 feet. 8.3 amps. The resistance, 1.24 ohms. And we get 8.23 volts.
I have a question about the test. Is when it's doing questions like this, is it going to be are they typically multiple choice, or are you just writing in the answers?
No, you'll have 4 answers. It'll be just like this. There will be 4 choices, and you're going to have to pick the one that you think is best.
Okay, awesome. Because I had to do process of elimination on some of this.
Well, you say it's not going to be 10. Well, it's not going to be 1.
Right.
So it's either B or C. So let's guess. Well, hopefully by the end of the class, you'll know enough and you'll be comfortable enough with this that it won't just be guesswork. But that's always one of the things with multiple choice tests is when all else fails, pick B. And that's but we know that when we make these exams, so don't count on that. So there's that rule with taking multiple choice, with instructors who are lazy when they're creating tests. You can often find that the answers are like 2 that are similar, 1 that's the opposite of the similar ones, and 1 that's a throwaway or a joke.
Mm-hmm.
Well, then the correct answer is one of them that's similar.
Mhm.
and pick the one that's longer, the answer that's longer, because it's harder to give a correct answer than it is to give an incorrect answer. So you need more words to give the correct answer, right? So that's how
What
you,
strategy for guessing?
yeah, I had a professor who had us show we could pass tests without ever reading the questions, just by reading the answers. So, yeah, that's how I got through college. What can I say? All right. So 6 solar panels are connected in series. Each panel has a VMP rating of 18 volts, IMP rating of 8.33. The voltage, the output voltage of this string is,
108 VDC voltage
right?
trick.
Now, why would it be DC?
Hmm?
Why is it DC instead of AC?
Because that was the rating in 818 VDC. It wouldn't just switch over to AC,
Yeah, that's true. And solar panels always
right?
generate
It
DC.
hasn't gone through the inverter yet.
Yeah.
Yeah, thank you.
Yeah. Solar panels always generate DC electricity. Fuel cells generate DC. Wind turbines actually, because it's a generator, generate AC electricity. You know, so we're used to seeing voltage just as volts, but now in this world we've got to know that is it volts DC or is it volts AC? Okay.
I have a somewhat unrelated question to AC and DC.
Sure.
When we charge batteries for like battery powered tools, like my battery powered Craftsman saws up there, when I charge those batteries, does the battery itself or does the charger have an inverter? Because the battery produces DC, but it charges on AC, right?
Yes, it's not an inverter. It's actually a um, rectifier. So what a rectifier will
Okay.
take the AC charge and convert it to DC. So it's
Gotcha.
through the rectification process. The inversion takes it from DC to AC. So yeah, your battery charger is basically a rectifier, you know, so, and a charge control.
Cool. Thank you.
Okay,
Yeah.
a kilowatt is
1,000 watts.
1,000 watts. Welcome to the metric system, right? Okay. Watts equals, this is the power equation.
Amps times volts.
Yes, watts equals amps times volts. When measuring the terminals of a blown fuse with a multimeter set to perform a continuity test, the reading will show what?
Resistance is equal for 1 or infinite.
Yeah, resistance is infinite. So what happens is when you're measuring, let's say you've got a long piece of wire, right? 3,000 feet long. It's on a cable spool or something, and you want to test it. You take one end of your multimeter to one end of the wire, you take the other end, and you can do a resistance test, and it will show you how much of the voltage has been lost as it travels that 3,000 feet. And you can think of that like if you're thinking about electricity like water flowing through a pipe, resistance is like the friction of the side of the pipe on the water as it flows. So it loses some pressure over distance, right? So you can measure it. But if you cut that wire or you opened up the switch or you blow the fuse, well, then nothing's going through, right? So resistance is infinite. It's 100%, you know? So typically they'll just say it's 1, you know, 1, or sometimes the meters will show a little INF digital readout. But most of the time, it'll just say resistance of 1 or 100%. So, all right, so that's everything you need to know about electricity. So hardly, but it's everything we need to know about electricity. So any questions or confusion on this chapter at all?
I'd like to ask about electrostatic dissipating shoes. Are those good to wear when working with electrical things?
Yeah, typically those are going to be, and the same thing can be like a mat, you know, as you enter into a room to dissipate any of the static. Oftentimes, like they might in a battery room, for instance, have a static discharge mat. But those shoes, I think, are really just going to be keeping you from building up a static charge on your body. And they'll often use those when you're working with sensitive electronic devices, where a little spark from your hand might cause it to short out, you know, a sensitive electronic, or in a clean room environment, or in batteries where batteries, they're storing charge and there might be hydrogen gas that's escaped. So any static discharge could actually cause the battery to explode. So that's possible, but we try and eliminate that through a well-ventilated storage cabinet or room. So it's not going to hurt, but for the most part with solar, it's not something people would invest in, because the things we're working with are not that sensitive, typically. Often they will invest in, when you're climbing around on a roof, they do have steel-toed boots that have grips, you know, on the bottom so you don't slide off the roof. So there are roofing shoes or boots that you can get, and that's something. And of course, rubber-soled insulation to isolate yourself from the ground is a good idea, because if you do touch a live wire, then you know you're insulated from the ground, and hopefully you're not going to die. You know, you may feel tingle, but hopefully you won't die. Yeah, all of those things would be considered personal protective equipment. And as we study some of the safety issues, for the most part, your employer is supposed to provide you with personal protective equipment, like safety glasses, gloves, things of that nature. But sometimes when it comes to like special boots, things like that, that's up to the employee to provide. So. Any other questions? All right, so I guess our next meeting will be on Tuesday, and we're going to jump into chapter 5. So now I think we get into the meat and potatoes of it. If you're moving forward and you run into any issues that you want some clarification to avoid frustration, just drop me an email, right? Because sometimes, you know, it can get complicated, and if you get lost at one point, then it just compounds itself. So none of these things are very complicated, I don't think, but there's so many of them, and you're essentially learning a new language. So there's a lot to absorb. Hopefully, or fortunately, we have a pretty good length of time here for you to work on it, as opposed to trying to get it all in 40 hours straight through. Okay, so I'll see you all on Tuesday.
Thanks, Jay.
Thanks, Jay.
Yeah.
Take care.